Welcome everyone to E2E's webinar series. And we are honored to welcome Harpreet Sahota, the popular host of Artists of Data Science. And he's also currently working as the Developer Relations Manager at DeciAI. He will be briefing us through the DeciDiffusion model, which is 3 times faster than Stable Diffusion v1.0. So, Harpreet, the stage is yours.
Sure. Let me just go ahead and pull up share my screen, my presentation here. All right. Sorry, I need to just find my presentation. There we go. And you should see the presentation now. Yep.
Yes, we can see that.
Awesome. What's up, everybody? Welcome to the session. Today we're going to talk about DeciDiffusion, but we're mostly going to focus on, what is latent diffusion models. We'll talk about Stable Diffusion 1.5. We'll talk about the challenges of Stable Diffusion 1.5, and then some cool training tricks that we had implemented using research that came out earlier this year to come up with an improved version of Stable Diffusion 1.5, which we call DeciDiffusion. A little bit about me. So I've got a kind of a diverse background in all things kind of quantitative. Graduated from graduate school about 10 years ago, a little over 10 years ago, and I studied math and statistics. Then I was an actuary for a while, took a bunch of actuarial exams. Then I realized that writing exams isn't what's going to get me paid. Took a detour, became a clinical trial statistician for a while, about 5 years. Worked as a biostatistician before moving into more kind of quote unquote traditional data science. Built 2 data science teams from the ground up. And then a couple of years ago, about 2.5 years ago, moved into this really interesting kind of role called developer relations, which is a nice blend between product engineering, marketing, content creation. So it's a lot of fun. I enjoy it. Tough role though, probably one of the most difficult roles in tech. So I've worked over the last few years. I worked at Comet, I worked at Pachyderm, and now I'm working at DeciAI. DeciAI, we build models. That's essentially, what we do. We've got a proprietary algorithm called, it's a proprietary neural architecture search algorithm, which we call the AutoNAC engine. And with this AutoNAC engine, we're able to create models that are data aware, hardware aware, kind of deployment aware, so to speak. This last year, we released several models. One of them is YOLO-NAS, which is a state-of-the-art object detection model. We've released DeciCoder under the Apache 2 license, which is a code generation model, 1 billion parameter code generation model. Also released DeciLM 6B, as well as its InstructTune version, DeciLM 6B Instruct. And we, just last week actually, had released a new state-of-the-art pose estimation model called YOLO-NAS Pose. And I'm happy to share links to starter notebooks with all of those at the end of this session. But that's enough about me, enough about Deci. Let me just give you an overview of what we did with DeciDiffusion. Long story short, DeciDiffusion is a 1.02 billion parameter text-to-image latent diffusion model. It was pre-trained on the Lion V2 dataset and then further fine-tuned on the Lion Art dataset. We used a lot of advanced training techniques to speed up training, improve performance, and achieve high-quality images at relatively low inference cost. And we're going to talk about all these techniques as we progress along through this presentation. So here's just a overview agenda, what we're going to talk about. So we'll walk through a comprehensive overview of just diffusion models in general, latent diffusion models specifically. Then we'll go into some lots of technical stuff, theoretical stuff, and then wrap up finally with a demo. And then as we progress, we'll kind of peel back each kind of layer of the technical techniques that we used. Sorry, the training techniques that we used to improve DeciDiffusion. But first, what the heck is a latent diffusion model? Good question. I'm glad you asked. So latent diffusion models, they're actually just an approach for generating high resolution images. So at its core, they function by mapping a data set's underlying structure to a simplified latent space. And one of the really awesome features of these latent diffusion models is that you could take a text description and convert it directly to an image. And this is leveraging something called a image generator network. And one interesting thing about this is this technique they use called progressive growing. So how this works is that a latent diffusion model can be trained on a set of low resolution images, and then gradually, as the training process progresses, you can increase the resolution of the images so that it then produces more high resolution outputs. This is nice because it allows for more the model to learn more fine-grained details of an image and generate more realistic results. So latent diffusion models have a wide range of applications, everything from enhancing image resolution to filling in missing image parts to upscaling image colorization, bringing the past back to life. Like there's a lot of great applications for these. So let's talk about Stable Diffusion 1.5. So Stable Diffusion 1.5 is a 1.07 billion parameter latent text-to-image diffusion model. Again, what do these do? Transform text description into photorealistic images. So how did Stable Diffusion 1.5 came to be? Well, it was initialized from the Stable Diffusion version 1.2 checkpoint. Then they took this checkpoint of this model and then they fine-tuned it for another 595,000 steps. So step is just how epoch is one the model traversing over the entire data set. Once a step is traversing over one batch of data, essentially. So it was fine-tuned on 595,000 batches of data at a resolution of 512 by 512 on what's known as the Lion Aesthetics V2 5+ dataset. During this fine-tuning stage, 10% of the text conditioning was dropped, and this helped enhance the classifier-free guidance sampling. And so the model combines a autoencoder with a diffusion model that's trained in the latent space of the autoencoder. It also uses a vision transformer, L14 text decoder for text prompts, and then has a UNet backbone for the latent diffusion model. Like, okay, what does all that mean? This is what it looks like. This is kind of a schematic diagram, right? So latent diffusion model is going to start with a rudimentary noisy image representation in some latent space. Then with text guidance, for example, a drawing of a pint of beer on a brick wall, the model is going to progressively refine this representation until it gradually unveils a denoised image representation. Then after several iterations, the representation in the latent space is then going to be expanded to a high resolution image. And so really there's three main components to a latent diffusion model. There's the text encoder. And the text encoder is just transforming text prompts into latent text embeddings. And then these latent text embeddings is going to be passed to a UNet architecture, UNet decoder. And so the UNet is a iterative encoder decoder mechanism that's gonna really introduce and reduce noise in these latent images. The UNet decoder uses some cross attention layers, and it conditions output on text embeddings that are linked to the description. And then finally, there's the variational autoencoder. This is going to transform the image into a latent representation and vice versa. So the encoder is going to convert an image into a latent version during training, while the decoder reverses this during training and inference. And it produces amazing results. It really does. The team behind Stable Diffusion 1.5, they did amazing work. But the model as they released it presents some challenges. So it's groundbreaking, of course, but it's lots of limitations, especially in terms of efficiency and quality of the images that are generated. So one is high computational cost. This is a huge problem in deployment, right? Because what does high computational cost translate into? translates into concerns with latency, right? That's going to affect real-time user interaction, right? The more computation it takes to generate an image, you're going to be paying more for each generated image. Your users going to have to wait longer to get their image. Um, you know, this tr ultimately translates into increased costs and dissatisfied users. Also, like the the inefficiency of this model, Stable Diffusion 1.5, uh, the inefficiency with respect to its like how it iterates and generates images, it just leads to more steps being required to achieve the desired image quality. This is because it uses linear beta schedules, which is really resource intensive. Well, we'll talk about the noise scheduling, but it's just an inefficient way to schedule noising. But then also the UNet that they use is very resource intensive. And so these two combined really compounds the inefficiencies of the model. Also, again, it's sample inefficient. So it means that you need more time steps during inference to achieve good quality results. So we saw these challenges, and we said, let's try to overcome it. So at Deci, like I said, we build models. We have a really smart research team, really, really intelligent folks working in research, and we have a powerful technology, the AutoNAC engine, which we use to create models. And so we said, all right, let's start with Stable Diffusion 1.5 and see what we can come up with. And so we ended up with a model that has enhanced efficiency. It's able to achieve the same quality in fewer iterations. We also pair it with what we call Inferi. Inferi is a proprietary runtime engine, inference engine, kind of like VLLM or Takeoff, whatever. But it's proprietary. And when we couple DeciDiffusion with Inferi, we get a huge increase in time savings and generation, 3 times faster, and we're able to produce high quality images more quickly. But this speed translates into actual cost savings. We're able to get a 66% reduction for every 10,000 images that are generated. A couple of things that we used was the introduction of the cosine beta schedule, and a more streamlined UNet, which we discovered using our AutoNAC engine, and we call this UNet NAS, and this really enhances the model's performance. So it's sample efficiency, it's noteworthy. We're able to produce top tier results with fewer diffusion time steps. So let's talk about this in more detail. First up is UNet versus UNet NAS. So the UNet in Stable Diffusion 1.5, it's like I mentioned, resource intensive. And if I could drill one point home, resource intensive means high computational cost at every iteration, right? But it's resource intensive both ways. It's resource intensive during training, and it's resource intensive during inference, because there's this repetitive noising, denoising process. And so, as I mentioned, using our proprietary neural architecture search algorithm, the AutoNAC, we found a new UNet, which we called UNet NAS. So UNet NAS, it has 2 fewer up and down blocks than the UNet used in Stable Diffusion. And another unique aspect of it is that you see here it's flexible, because you can adjust the composition of each block. So you can then optimize the number of ResNet and attention blocks so that you're able to get maximum performance with really minimal computation. And so with this UNet NAS, we're able to reduce the parameter count of the model. And of course, if you reduce the parameter count of the model, what happens? You get improved computational efficiency. And if you get improved computational efficiency, what happens? You get a more resource efficient model. And so we're going to dive into the UNet a little bit more, but kind of a sneak peek is that this UNet, we trained it on a 320 million sample subset of the Lion dataset, and then we fine-tuned it on a 2 million sample subset of the Lion art dataset. And then we use some specialized techniques to reduce training time and achieve high quality images in fewer iterations. So DeciDiffusion essentially has the same foundational architectural elements as Stable Diffusion 1.5. Like it's got the variational autoencoder and the clip pre-trained text encoder. And our primary innovation was just the substitution of the UNet for a more efficient UNet NAS. That's really the biggest thing that we did. And so this new component then streamlines the model by reducing the number of parameters, which again leads to greater computational efficiency. And we trained this model right here. This is our architecture, right? We trained this architecture in 4 phases, and these are the phases. Phase 1, trained it from scratch on 1.28 million steps at resolution of 256 by 256 on a 320 million sample subset of Lion V2. Phase 2, we then trained for 870,000 steps at a resolution of 512 by 512. So this is that progressive growing I was talking about. And we did this on the same data set, same exact data set. And so what happens when you do this progressive growing, right? We trained on smaller resolution images, and then we trained on those same images, but at a higher resolution, so that we're able to learn more fine-grained detail, more kind of information, so to speak. Then phase 3, we trained for 65,000 steps with exponential moving average. And then we used a different learning rate schedule and a more qualitative data set. And then we fine-tuned on a 2 million sample subset of Lion art. Some more details with respect to training. So like I mentioned and have been mentioning, we used training techniques to shorten the training time and arrived at higher quality images in fewer iterations and steps. So you guys are probably wondering, man, I keep talking about these training techniques. What the heck are they? I know. I'll get to them right now, starting with technique 1. So the UNet NAS, remember, the UNet NAS, we trained it on a 320 million sample subset of the Lion dataset, and again, fine-tuned it on a 2 million sample subset of Lion art. We actually only trained the UNet part of the latent diffusion model, right? So we didn't need to compute the VAE latents or the clip embeddings for every time, for every image. So we compute them once before training, and then we cache these stored versions and we use them later. And so now this way we end up saving about 25 to 50% of computation at every epoch. So Stable Diffusion's VAE, what we're able to get from their variation autoencoder is just some summary statistics about the data that they have, right? So we're able to get the mean and standard deviation, right? So the average values and the spread of the data. We store these values and we use them during training. And so we're able to add some randomness to the process, even when using data that we've prepared in advance, right? So it kind of driving that point home, right? So we compute these embeddings and latents, right, once during training, right? And then as we progress in epochs, we then use the summary statistics from Stable Diffusion's VAE and perturb each image during training, right? So we don't have to, we just add that bit of randomness into the image during the training process. So we don't have to do it for every single image every time. Another technique that we used was we didn't use exponential moving average throughout the entire training process. And we found that when you use exponential moving average, the initial changes to your model weights, they're just not going to affect the final output that much. EMA is expensive, right? Because you need to store extra weights on disk, and then you need to spend time aligning these sets of weights. And this time adds up, right? Because given how long training takes, it just ends up not being worth using exponential moving average for the bulk of the initial training steps. And so by not using it during the initial training steps, we're able to handle bigger data batches and then speed up training by 15%. So we only use exponential moving average during the last 5% of the training iterations. So as you can see here, we're able to get a bigger batch size. Bigger batch size means faster training. So now let's talk about some techniques that we use to generate nice images, like really high quality images with fewer iterations. So this entire section really is about sample efficiency, and how we're able to produce high quality results with fewer diffusion time steps during inference. And so let's get into those techniques. So one technique was to enhance intermediate step performance. So we just looked at refining steps involved in the actual diffusion process itself. So with stable diffusion's beta scheduling, we found that we could skip like 1/3 of the final steps without a major drop in the FID score. Uh, FID is a metric for gauging the quality of text to image models. Uh, so Farish inception distance, FID score. And so we found that, you know, that the linear beta schedule that Stable Diffusion used, it's really not making the best use of the model's learning potential. So the model is just it's during some of the time steps is just turning random noise into different random noise, which is not useful. Wow, like that's a waste of computation to take random noise and then turn it into other random noise, because we want to take random noise and turn it into nice images, right? And so we switched to a cosine beta schedule. And so the cosine beta schedule was pioneered by A. Nicole and P. Dhariwal in a paper called Improved Denoising Diffusion Probabilistic Models. And so using this technique, we're able to better harness the model's learning capabilities. So this means now that our model is able to kind of more accurately determine how much noise is actually added to the image. Right? If we're able to more accurately determine how much noise is added to the image, then we're going to have better noise predictions. And if you have better noise predictions, the model knows what to subtract out to generate high quality images, right? So sharper noise predictions speeds up the image generation process. So now we're able to have a model that operates more efficiently and produce images of better quality. And here's kind of what I mean by turning random noise into more random noise, right? So let's double click on this part. So in the linear schedule, noise is added uniformly at each time step. So this means that the images become almost purely noise towards the end of the diffusion process. And so you can see that here at the top of the top row. And so the real problem here comes during the reverse process, because in the reverse process, the model is essentially trying to recreate the original image from the noisy image. As you could see here on the linear uh, schedule, like a lot of those steps are just converting one type of random noise into another type of random noise. And this just does not contribute to the final image quality at all. These steps are redundant. But when we're able to use a cosine schedule, we're able to vary the noise addition in a non-linear manner. And this is ensuring that every diffusion process step is meaningful and is contributing positively to the final image quality. And so just a word here about, optimization of model capacity. So model capacity, it refers to the model's ability to learn and represent complex functions or patterns of data. With the linear schedule, model capacity is not being fully utilized because some of the steps are redundant. This is going to lead to overfitting and a lot of inefficiency. Cosine schedule, it's more complex, but it's like challenging the model throughout its learning process, right? And so this ensures more robust learning experience, and we're able to better utilize the model's capacity. And so like it should be clear here that due to the redundancy in the linear schedule, we're wasting computational resources, and this becomes evident during the reverse process, because you can see some steps are just taking one type of noise turning into another type of noise. And so since the cosine schedule Every step is meaningful, so the model is able to work faster during inference, and it produces outputs without going through all the usual steps and still achieving some good results. So we combine this technique with the technique of cosine beta schedule with the technique here, min signal to noise gamma loss weighting. And this was introduced in a 2023 paper by T. Hang and others called Efficient Diffusion Training via Min SNR Weighting Strategy. And so this Min SNR gamma loss weighting strategy, it's just designed to optimize the training of the diffusion model. So it's assigning weights to each time step based on that time step's difficulty. And then it uses a clamped signal to noise ratio as the determining factor for those weights. So essentially what the strategy is doing is it's recognizing that not all time steps in the diffusion process are equally challenging or critical to the final image generation. And so there's these intermediate steps. And in these intermediate steps, this is where there's a lot more intricate patterns or subtle details. And these are the things that you want your model to learn, right? And if we assign these intermediate steps greater importance through this weighting strategy, we're able to guide the model to focus more on those steps. And this, like, of course, is going to, lead to more robust learning and more better understanding of kind of, the data distribution, just better diffusion process. Um, and so while we emphasize the model to quote unquote focus on those intermediate time steps, the time steps that are characterized by minimal noise, those get downweighted. So not as much importance on those. And so the decision here is just rooted in the understanding that minor noise variations are less perceptible to human eye. And if we de-emphasize those steps, then we're ensuring that the model doesn't waste resources on aspects that have a limited impact on, a human's assessment of the quality of those generated images. So just to sum up this slide, it's just a deliberate and calculated approach to balance the model's focus across the diffusion process. And we direct its attention to the most impactful time steps and ensure that there's the optimal use of the learning capacity so that we can generate really good images. So next, I want to talk about techniques that we use to capture the data distribution. One, progressive distillation. So training and inference procedures were optimized to capture the data distribution better. So if we're able to accurately capture the data distribution, it becomes really critical when you are wanting to be in a inference regime with few time steps, right? So this is going to be critical for that part. So our optimization was influenced by the findings of Sanchuan Lin et al. And others in a 2023 paper that was called Common Diffusion Noise Schedules and Sample Steps Are Flawed. And so their team identified a lot of inconsistencies in prevalent diffusion noise schedules, and this led to models producing, kind of medium brightness images, even when the prompts suggested otherwise. So they achieved a kind of a more harmonious alignment between training and inference by ensuring that a terminal signal to noise ratio, a zero terminal signal to noise ratio, and implementing other fixes like adjusting the noise schedule, switching to V prediction, which we'll talk about next, and then always sampling from the last time step. And this alignment is very important, especially, again, I'm drilling this point home, when you want to operate in an environment, in an inference environment where you want to generate images with a limited number of time steps. And so this, meticulous attention to detail it's ensuring that the model is generating high quality images and that it's, being remaining versatile and responsive to a wide range of prompts. And so when we're able to better capture the data distribution, you can confidently produce visually appealing images that align with the intended prompt, even under the constraint of limited number of inference time steps. V prediction. So here's a breakdown of how V prediction works. So imagine you have an image that's covered in noise that makes it look blurry or distorted, kind of like the far left of what you see on your screen here. That noisy image is the starting point. So typically the model is going to try to remove the noise step by step and gradually reveal that clear image underneath. It's kind of like peeling layers of an onion. But with V prediction, the model is taking a different approach. So instead of peeling back the noise one at a time, essentially the model is going to guess what the clear image is going to look like in just one go. And so the noise isn't discarded, it's used as a hint or as a clue. So a model looks at this noise and tries to figure out what the original image might have been. So it's trying to like kind of guess like the original picture of a jigsaw puzzle just by looking at scattered pieces, right? Then in the final step, again, the model isn't just trying to remove random noise, it's actively trying to predict or guess the clear image based on the hints provided in the initial noise. Then we use another method called epsilon prediction. Well, I guess just to compare it with another method called epsilon prediction. So epsilon prediction, the model is just slowly and gradually removing noise over several steps. So it's a more cautious approach, but it's taking time to reveal a clear image. But with V prediction, you just aim for a more direct and efficient route to clear image. And so traditional methods might struggle in this case, but V prediction is just giving a more robust solution. So the research team here, we recommend always using V prediction for the model. And you can adjust parameters like gamma sub t to achieve some different weights if needed. Different loss weightings if needed. And additionally, when we're able to sample with zero terminal signal to noise ratio, um, it's crucial that you handle the V prediction correctly to avoid any potential issues. And so another optimization strategy here. So there's a question that came up for 1.2 billion images, how much space and memory will it consume on a hard disk? It's a good question. Short answer, a lot. Um, I don't know the exact number, but we can look that up. Actually, we'll look it up if you just type in Lion data set size. I think it's something the petabyte scale. So optimization strategy here. Another optimization strategy was that we skipped step 0. So we wanted to produce clear, more varied images. And so we adopted the strategy that was inspired by, again, Sanchuan Lin and others in that 2023 paper that I mentioned before. And so a key element in their strategy is intentionally skipping step 0, which is the final step in the reverse diffusion process. And so why is this important? Well, because the noise level at this step is so subtle that it's like virtually indistinguishable to the human eye. So this means that the images that's produced at time step 1 look almost identical to what you'd get if you'd included time step 0. So by skipping time step 0 during the image generation process, we're deciding where to focus our model's kind of energy and resources, so to speak. So instead of wasting effort on that last step that doesn't, noticeably change the image, we can concentrate again on those intermediate steps that matter the most. And so the results are that these these are the steps that are going to shape the overall image look and content. So again, our model is able to produce images with crisper details and showcase various features and styles. And this approach, it really underscores the significance of those earlier steps in the process that help determine the final image content and structure. So here, just a kind of a side-by-side comparison of the same prompt and the generation you get with DeciDiffusion versus Stable Diffusion 1.5. And so based on a subjective evaluation of surveys and FID scores, so based on a subjective evaluation surveys and the FID score, which is not subjective, DeciDiffusion's 1.0's quality at 30 iterations it's either on par or better than Stable Diffusion 1.5 at 50 iterations. So on average, DeciDiffusion generates images after 30 iterations. The images that we're able to generate after 30 iterations achieve a comparable FID score to those generated by Stable Diffusion 1.5 after 50 iterations. So again, FID is used, that's the Fréchet inception distance. This is used to assess text to image models, and it just compares the distribution of model generated images with the real or ground truth images. So lower FID score is taken to signify that the generated images have a closer resemblance to the real images. So for our study, we chose 10 random prompts, and for each prompt, generated 3 images by Stable Diffusion with version 1.5 that was configured to run for 50 iterations, and 3 images by DeciDiffusion that was configured to run for 30 iterations. We then presented 30 side-by-side comparisons to professionals who voted based on adherence to the prompt and aesthetic values. And the results of those votes are here. So DeciDiffusion at 30 iterations exhibits an edge in aesthetics, but it's on par with Stable Diffusion at 50 iterations. Here's just the improvement on latency. So if we compare PyTorch to PyTorch model, we're 2.2 times faster. When we talk about the inclusion of Inferri, Inferri is our proprietary runtime engine, we end up being 3x faster. What does this mean? Money back in your pocket. So this improved latency, it's attributed to its advanced architecture, efficient training techniques, and the integration of Inferri. So the combination of these 3 components, it just provides hardware flexibility. And so we're able to shift from a high-end A100, H100 GPU to a more cost-effective A10 without compromising performance. So again, compared to Stable Diffusion on identical hardware, DeciDiffusion is affordable and it costs 66% less for every 1,000 images generated. We can also reduce, obviously, reducing computation, we're reducing the negative impact of carbon emissions as well. So I'll give you guys a second to pull these up. QR codes, take a screenshot, whatever you need to do. This will take you to our Hugging Face space. Do like the Hugging Face space, please. That's going to support the awareness. Here's the model card on Hugging Face. Please do smash a like on the model card. We're going to get into some notebooks that you can just pull up as well. So here's a link to that notebook. Take a screenshot, do whatever. That is a duplicate slide. And then finally, come and hang out on Discord. So I have a Discord community, Deep Learning Daily. This is a community, there is entry criteria for this community. If you have not been working in deep learning for at least 1 year, then this probably will not be the community for you. Whether you're into language models, computer vision, generative AI, doesn't matter, all things deep learning, they just ask that you just have, we want to create a space for more experienced individuals. So thank you very much. And so let me give you guys a link here. So this is a Hugging Face space that you guys can check out. I'm going to keep the Hugging Face space open for a little bit longer. So maybe by the end of the weekend, I'll shut this thing off. But you can test it out here on the A10 and see exactly what how it works. So, but like what's a good generation? Let's say a 1969 Chevy Camaro, baby blue, rolling down PCH
I
at
think
sunset.
Harpreet, you're not sharing your screen.
Oh, I'm not. Oh,
No.
oh, yes, you're right. So this is the DeciDiffusion Hugging Face space. Check it out. Smash a like. I hope to see this number move up from 74 to something higher. So all 18 of you left, go smash a like, get us to 100. Um, but here I just did 1969 Chevy Camaro, baby blue, rolling down PCH at sunset. Let's see what happens. And this is quite nice. That's probably Channel Island in the background, and there we go. We could also kind of switch around. Of course, we can say oil painting. I don't know how to spell aesthetic, but oil painting, and see what happens. And you can see we're able to generate images quite quickly. Um, and so I guess there's questions coming in.
Yeah, Sharath has a question. Can this
Oh,
coexist?
yes, that's a good
Yeah.
question. And so I'm going to show you this right now. Actually, I think you're going to pull something up here, right? You're going to pull up the notebooks
Yeah.
for me.
Yes, yes.
Okay. So I
Oh,
gave you three notebooks. Let's go through the notebooks one by one to address that last question. That's gonna be the last notebook we look at, but are you gonna share your screen now?
yes.
Okay. So let's pull up the DeciDiffusion notebook itself, just to kind of walk you all
Can you
through that.
see my screen?
Yeah. Yeah, I can see it. Great.
One
Great.
second. 1 second. Hold on. Yeah. So this was a notebook that I ran
Okay.
based on your code.
Yeah, so this is the DeciDiffusion notebook, right? Do you mind if let me see something here? Can I request remote control and
Yeah.
walk through here? All right.
Yes.
All right. Great. Great. Cool. So let's take a look at this notebook. So this is just how to use
Comparison
DeciDiffusion.
between.
Yeah,
Yeah.
this is just how to use DeciDiffusion in Hugging Face. So if you're not familiar with how to programmatically work with a diffusion model, that's what this notebook will show you how to do. And hopefully you see that it's not that scary. And you can see how long it takes to generate images. Wow, this is quite quick. What kind of GPUs are you guys using here
We are
at
using 800 only. Yeah, it's quite
okay,
fast. Yeah.
A100s? All right, great. So you can see it's super quick to generate images.
Yeah.
Um, and when you compare it to the generations taken, I do the exact same prompts. When you
Yes.
scroll down further, we do the exact
Yes.
same prompts compared with stable diffusion, and you can see how long stable diffusion takes compared to how long we take, and it becomes a lot quicker. So about half the time. And I personally think that our images are a little bit better.
Yes.
Did you run any of the other notebooks?
Yes, I did.
Okay.
This one. Oh, this one generated an error. Yeah, this one. I was able to run only 2 notebooks.
Okay.
Let's see if this one
So
is. I didn't have enough time to,
okay.
enter
Yeah,
the
yeah.
comments.
So this notebook is uh I'll just share the links to the notebooks with everybody that I did here. But this is an image to image, just showing how you can take a diffusion model and convert it to an image to image diffusion model. So that's what this notebook is showing you how to do. So I took DeciDiffusion itself, and it's a text to image model, but then I turned it into an image to image model. So we started off with this image up here, right, and then um, turned it into a different image, and then the full notebook I have, um, the full notebook I have will have a lot more
Yeah.
guidance there. If you don't mind, I'm gonna
Yeah.
stop the remote control.
Yeah. Okay.
Let me just share my screen just to show folks.
Sure.
But
Sure.
yeah, end to end networks looks like they have some really fast GPUs that you can use. I don't know what pricing is or whatever, but check it out. Um, so let me just drop some links here for everybody. And I think you can probably just upload these notebooks as is right into end-to-end networks and run
Yes,
them.
E2E network.
So
Yeah, right.
E2E network, sorry. So this first notebook I'm sharing, sorry, this needs to be shared with everyone, host and panelists. How do I share with everyone? Well, either
Uh,
way, um, we'll get these notebook links out to you. I hope.
yes,
Um,
yes.
so this right here, this notebook will show you exactly how to use diffusion model programmatically with Hugging Face diffusers. And this notebook will show you how to take a diffusion model and turn this into a image to image model, breaking it down kind of step by step. Um, I think this one's actually a blog as well. So I work at DeciAI. If you go DeciAI and you type in image to image, it should take you to my blog here. Whatever, image to image DeciDiffusion, you can find it. And so this will show you exactly how to do that, how to take a diffusion model, turn it into image to image model. Now, this is the interesting part here. Unfortunately, I wasn't able to run this notebook in time. But to answer Shard's question, can this coexist with a computer vision model? Let's say object detection. So yeah, and I want to show you this. So like I said, we build models at Deci. We released a bunch of models, um, this year, a lot of models this year. One of which is a object detection model called YOLO NAS. We also released a diffusion model that I just talked to you about, and then hopefully I'll be back if you guys will have me back, and I'll talk to you about um, our language model, and specifically I'll teach you how to fine tune that language model.
Definitely. We are looking forward to that.
Yeah. So this model, this notebook here, essentially what I'm doing is, okay, you'll be asked to either upload a image or pass in a URL to an image. Once you upload that image and pass the URL to it, we're going to perform some detections. And then we're going to take those detections that the model produces, and then I'm going to pass that to the language model. And the language model is going to generate a one sentence story. And then I'm going to take again that one sentence story, pass it again to the language model, and ask it to come up with a diffusion prompt. And then I take that diffusion prompt and I pass it to DeciDiffusion. So this is kind of the process I'm going to show you right now. So you're going to get a crash course in like prompt engineering, kind of. So this right here, this is just downloading the models. Essentially, that's what this does. Then we have some helper functions here and some prompts. So this prompt, I'm instructing our DeciLM6B instruct to create a one sentence story. So the model will get detections like this image has 3 bicycles, 1 person, and a stop sign. And so I give this model examples of one sentence story. Like, what are the good qualities of a one sentence story? An example of a one sentence story. Here's the contents of the image. Give me a one sentence story. And I was like, for a DeciDiffusion 6B is 5.7 billion parameters. It's not very big, but I was like really, really blown away by some of the one sentence stories this thing was able to generate. So play around with it. Then we take that one sentence story, and then I have a prompt and I send this back to the language model, and I say, here, create a create the uh, prompt for a diffusion model. So what's the characteristics of a good prompt? Here's some examples of good diffusion prompts, and it's able to generate a diffusion prompt for me. So these are just helper functions that are you can read about them. Sorry, I didn't put doc strings, but they should be pretty self-explanatory. Then we start by using YOLO NAS to detect what's in the image, and then we use DeciLM6B instruct to come up with a story. And so this is different types of prompting, knowledge generation, and few shot prompting. So this is just
Harpreet,
types of
there's
prompting.
another question.
Uh,
How do you overcome copyright issues by Amit Kumar?
So as people that we just train models, right? So, we use data sets that have been provided, and we'll use those data sets, right? We're releasing models under essentially permissively licensed use cases. It's up to the end user to handle copyright issues by themselves, right? So we're just using publicly available data. Lie-on data sets are publicly available. So the copyright issue comes back to you and how you use it in your application, because we can't assume all those. Um, we can't assume all those. What's sort of looking for liabilities, right? We're essentially just training a model, putting it out there, and it's up to the end user how they use it. Where can you find a resource for AI ML prompt engineers? That's a great question. I actually next week I will be at well, the week after next week, I'll be at LinkedIn Learning Studios recording my second course. My first course was all about computer vision. So if you have LinkedIn Learning, just type in computer vision. Mine should be the newest course. Second course I'm releasing is called Prompt Engineering with LangChain. And this is it's not. I have thoughts on this. Prompt engineering is actually engineering. It's not just like opening up ChatGPT and typing in a string and getting a string back. There's actual engineering that needs to be done. So that course will be recorded at the end of November, likely out by early January or February, something like that. Probably February, I think it'll be out. So if you have LinkedIn Learning, you can take it for free. Other people will charge you like $800 to take the same course. So yeah. And yeah, that's pretty much all I had to say about this notebook. I thought it was fun to do, and this is the image it generated. So I cleared the output, so I don't. Oh, okay. Let's see. So do I have any? No, I don't have the example of the actual story and the prompt that it generates. Well, here's the prompt. Uh, this was the one sentence story part, right? Uh, a man races his motorcycle through the city, chasing the car that left him behind, right? So that's the one sentence story that it generated from the image detections. And this is the full prompt that it generated for the diffusion model, captured in hyper-realistic sculpture style with fragmented figures, distressed materials, and a surreal, otherworldly color palette. And you can see that it does kind of adhere to that. So I thought that's pretty cool. So yeah, check this notebook out as well. I turned it into a blog as well. So if you go to DeciAI, go to resources, go to blogs, everything that I write is here. So here's that image to image. Here's a blog I wrote on how to instruction tune language model. If you're into Llama Index, here's how to do that. And the blog that you would want to is this one right here. So yeah, that is it from me. Thank you very much.
Yeah, it was a great session, Harpreet. Any
Yeah.
questions, anyone?
While you guys are thinking up questions, so I talked all about how you can, get in touch with me through Deci's channel. If anybody wants to get in touch with me personally, follow me on Twitter, Data Science Harp. I have a newsletter that I publish every either Saturday or Sunday called the Generative Generation. So that's you can just do that by going to harpreetsahota.substack.com, and that will take you to the generative generation. So hopefully ETE networks can share a link for that. 17,000 subscribers so far. So I guess people must enjoy it. So yeah, check it out and hear my
Yes.
thoughts if you're interested in hearing my thoughts. Doesn't look like there's any questions coming in.
Uh,
Oh,
yeah, one question. Okay,
follow me
no,
on
that's
LinkedIn. Right on. Hey, thanks. Thanks for following me on LinkedIn. LinkedIn, LinkedIn is not my favorite platform at the moment. But follow, subscribe to the newsletter. We'll be in touch. Cool. Well, thank you so much for inviting me, and take
and
care,
it was an
everybody. And
honor to
hopefully,
host you.
thank you. Yeah, hopefully next time, I'll have more time to do this stuff on your guys' platform. Maybe with the next session. Who knows? Cool. Take
Cool,
care, everybody.
thanks. Thank you.
Oh, which platform am I more approachable? I pretty much like Discord is the best way to get a hold of me. Like, uh, messaging me on LinkedIn, your message will inevitably get buried, and I don't check messages there often. So Discord, um, that's the best way. So deeplearningdaily.community will take you to the Discord, and I'm available there.
And can we have your email?
No, just find me on Discord. I'm on Discord because even email I don't check. Even email, like I try not to be distracted by communications because I have so much thinking and coding to do. Um, so in general, getting a hold of me is very difficult, as the as the EDE team can attest to. But yeah, appreciate you
Yeah.
guys though.
Okay. Any more? Oh, okay, thanks. Thank you.
Cool. Take care, everybody. We'll see you around.
Thank you.
Bye.
Thank you. Bye.